So hello everyone, welcome back to another video of mine in which I will be discussing today about the integrated rate equation. Now this is just a continuation of probably a discussion, or if you guys have a background knowledge about rate law, then this is just a continuation of this discussion, which is the integrated rate equation. Now if you guys can recall that rate law can be used to determine actually the rate it's used to determine the rate of the reaction. So it's gonna use the rate constant, which is the K, and the reactant concentration. So just a quick recap for everyone. This is the formula for the rate law. Reactants. So, yes. So rate, the rate law can determine the rate of a reaction using the rate constant, which is K, and the concentration of the reactants. So sometimes we are given first order, second order, third order, etc. And again, when we write first order rate law in first order, it's just R is equal to K A times the concentration of A. So this is the first order. I'll leave it. This is first order. And for second order, it's just A squared. This is for second order. And I'll just elaborate to order of the reactions so that it'll be easy for everyone. So it's written, or in general formula, or the generic formula is just like R is equal to K A X B Y. This is actually the general formula that our teacher gave us when she introduced us rate law, where X is the order with respect to A and Y is the order with respect to B. So I hope you get it. Now, again, it can actually be used to determine the concentration of a reaction, or the concentration of a reactant at a specific time during a reaction. And yes, so the difference is what's the difference between the rate law and the integrated rate equation? Now, as you can see, the rate law, this one, I'm gonna draw a box so that you guys can see. Okay, if you can notice that there is a rate constant and of course concentration of the reactants, and both of them are present in the integrated rate equation and rate law. It's just that time is included in the integrated rate equation. So rate can actually be written as R is equal to delta A, concentration of A, over delta T. Oops, my mistake. It's negative delta A over T, negative delta A over delta T, which is it's just like rate constant times the molar concentration of A. So we can actually write this one for our rates. So yes. So let's discuss first about the first order reaction. The first order reaction. So the first order reaction, it has two formulas that can be used when you are solving a problem. You can use the natural log of A delta T, A times T is equal to K times negative K times T plus natural log of A subscript 0. Take note, guys, that A sub 0, or the concentration, is this one is actually the initial concentration, whereas A subscript T is the final concentration. And this one, negative K, is our rate constant. I'm sorry for a bad handwriting. And T is time. So these are the things that you need to know in the first in integrated rate equation. This is the first formula that we can use. I hope you guys can see because I can't see. Yeah. So again, natural log of AT is equal to negative KT plus natural log of A subscript 0. Whereas the variables that we're going to be using is the AT, which is the final concentration of the reactant. We have the rate constant, we have the time, and lastly is we have the initial concentration, which is written as A subscript 0. Okay. Or, I mean, the second formula that we can actually use is, sorry, I hope you guys can still see. Oh my days. Yeah. So, yeah. Okay, anyways. We can actually use another formula, which is natural log of the final concentration over the initial concentration is equal to negative K. Now, using these equations, guys, we can actually manipulate them to find the given. So it's up to you how you're going to use your algebra, as long as you're going to use this formula. And by the way, when you're actually asked to solve a problem, you are given or you are told that this reaction or this problem is in first order or rather in second order. So it's actually given. It's just that you need to take note of the formulas that you that I've written, since it's going to be used in future quizzes. Okay. So yeah. So let's go first. Before we proceed to the some problems about the integrated rate law in integrated rate equation in first order, let's discuss first about its what they call this, like in linear equation. So actually, this one, n a t is equal to negative kt plus n natural log. So actually, this is just similar to the form of linear equation, which is like y is equal to mx plus b, where your slope is the k, negative k, and your intercept is the natural log of the a concentration. So if you're going to graph this one, negative k is your slope, and this is your y-intercept, if I'm not mistaken. No, y-intercept. Yeah. So yes. So the line, or its what do you call this, illustration, looks like this. I'm sorry for my bad handwriting, guys. Okay, this one. Sorry. So it's negative k. This is natural log of a initial concentration. Then slope is k. Oh my god. Sorry. Okay, this is it. I hope you guys can see. So anyways, guys, let's try to solve. Oh, by the way, my mistake. Yes, it is indeed. Again, let me repeat that in the graph of a first order reaction, we're asked to determine whether this graph is first order or second order. The graph of the first order reactions are the slope are always like this are their slopes are always negative. It's negative k, and their y-intercept or b is the natural log of the initial concentration, which is denoted as a subscript O, or 0 rather. So let's proceed to the problems. Okay. So I have here this one. Actually, I hope you can see. So the reaction A produced products is a first order with a rate constant K is equal to 0.0279 per minute. If initially the concentration of A is 0.500 molar, what will be its concentration after 618 seconds? Now, again, this is first order according to the problem. Now let's write the given. So the given is actually it's 0.0279 per minute. So we can actually write this in fraction. This is still the same as 0.0279 minute to the power of -1. This is it. And the initial concentration is 0.500 molarity. I'm sorry. So these are the given. And oh, I forgot that we have also the time, which is 618 seconds. Now, As you can see here, everyone, that the rate constant and the time, the given rate constant and time, their units are different. So what we're gonna do is we're gonna convert either one of them so that both of them can be used in the equation. They can be, similar so that we can use them. So for this case, let's convert time since it's easier. So what we're gonna do is we're gonna convert time to minutes. So as you can see, the given here is in seconds. We're gonna convert it to minutes. So it's very simple. Again, 618 seconds, just for illustration so that everybody can understand. 618 seconds times 1 minute over 60 seconds. So it's actually 10.3 minutes. So this cancels. That will give us the answer 10.3 minutes. So both units are the same. So now we can actually use the problem. We can actually use one of the equations that I've taught you earlier. So yes. Now back at it again. So I introduced two equations that we can use in first order reactions. This is either this one or this one. Now, it's up to you if what equation you're going to use. But you can also use this or you can use this. But for this problem, for your life to be much more easier, you're gonna use the first equation that I give you. So let me write it. So natural log of the final concentration is equal to the negative rate constant times time plus the natural log of natural log of the initial concentration. Again, this is the final concentration, the initial concentration. So what we're gonna do is we're gonna substitute the given values to the equation to get our answer. So yeah, ln AT is equal to, since negative k, of course we're gonna make 0.0279 per minute to negative 0.0279 per minute. So it's 0.0279 times, of course, in minutes, 10.3. Since this one is minutes, this one is minutes, we converted it from seconds to minutes. And plus the natural log of the initial concentration, which is 0.500 molar. So using your calculator, everyone, please look and listen. For this case, okay, first things first, you're gonna find the natural log or L in your calculator. Then you're gonna input your answer first. So ln 0.500 molarity, so it gives us negative 0.693147 or some number. It's up to you. Then right after the bat, you're gonna add it to the negative KT. So we're just gonna use our calculator. So of course, don't forget the parentheses and the operation. Negative 0.0279 times 10.3. Okay, that gives us negative 0.9805. So ET is equal to negative 0.9805. So we're just gonna, it's for decimal places only. Now we're done here. Since we need to remove the natural log, since we cannot have our answer, we cannot have this one as our answer. So recall that a natural log is just log base of e x, if I'm not mistaken, equals to y. Now we can actually convert this one into an exponential equation. So we can just use x is equal to e raised to the power of y. Y is like a, but anyways, Again, we can convert this one to x is equal to e raised to the power of y for everyone's life to be much more easier. So in this case, 80 is our x, and of course e raised to the power of negative 0.9805. Now, using your calculator, if you guys have a similar calculator like mine, then all you have to do is shift ln. That gives you e raised to the power of something, and you're just gonna input a number. So in this case, e raised to the power of negative 0.9805. That gives us 0.375, and this is our final answer for the final concentration after 618 seconds. This one. This is the answer. Okay? Okay, let's go to another problem. Okay, don't mind my computer, everyone, or don't mind my setup, but let's solve this problem. It's another first order reaction problem. So the decomposition of a certain anticide in water follows first order kinetics with a rate constant of 1.45 per year at 12 degrees Celsius. A quantity of this anticide is washed into a lake on June 1, leading to a concentration of 5.0 times 10 to the power of negative 7 grams per cubic meter. Assuming that the average temperature of the lake is 12 degrees Celsius. So first, what is the concentration of the anticide on June 1 the following year? Now, there's the answers, but we're going to solve this one. And the second is, how long will it take for the concentration of the anticide to decrease to 3.0 times 10 to the power of negative 7 gram per cubic meter? So guys, so we have the given. I'm sorry again for the setups, it's so messy. So anyways, we're given the rate constant and the initial concentration. The rate constant is 1.45 per year, and the initial concentration is 5.0 times 10 to the power of negative 7 gram per cubic meter. So we are asked two questions. So first, let's solve this one. What is the concentration of the anticide on June 1 of the following year? So we're asked for the final concentration. Now, what we have is K 1.45 per year and the initial concentration of 5.0 times 10 to the power of negative 7 gram per cubic meter. Now, what do you call this one? Yeah. So, oh my days. I'm sorry. Okay. So, we're actually here in this one. We can actually find time, since we're asked what is the concentration of the anticide on June 1 of the following year. So, meaning of the following year, it's just equal to 1. We no longer have to convert it to like 365 days or whatsoever, since again, the units are the same. So, it's as is. So, this is still in first order. So, still the same formula that we're going to use. This is natural log of A subscript T is equal to KT plus natural log of the A subscript 0. So, this is it. We're just going to plug in ln is equal to AT, since this is what we're going to look for. And K is, of course, negative 1.45 times 1. So, again, we're asked about on the following year. What is the final concentration of the anticide on June 1 of the following year? Of the following year means next year. So from June 1 this year to another June 1 next year. So just 1 year. Okay? Then plus natural log of A sub 0, which is the initial concentration, which is 5.0 times 10 to the power of negative 7 gram per cubic meter. Again, oh my god. Again, using our calculator, we can just use this one. Okay, sorry. Negative 1.45. I'm sorry. 1.45 times, oh my days, times 1 plus natural log of 5.0 times 10, oh my days, times 10 to the power of negative 7. I hope I got it right. So we got our final answer. We got our partial answer, negative 15.96. Negative 15 point. Oh my god, sorry. Negative 15.96. So n is equal to A subscript T is equal to negative 15.96. Okay. Now Again, we're not yet finished here. We're going to convert this one into an exponential equation. So again, AT is equal to E raised to the power of negative 15.96. And that gives us how much? Again, shift ln and raise the power of something, in this case negative 50.96. Okay, so our final answer is 1.17 times 10 to the power negative 7. So of course we still need to follow the rules of the given figures. So oh my gosh, hope you guys can see. So 1.45, 5.0, so the least decimal places, or the from the given, we're gonna use two significant figures since it has only 2 and this one has 3, so we need to use the least number of significant figures from the given since this is multiplication and division style. So in this case, since our raw answer is 1.17, we're gonna round it off so that we get an answer of 2 significant figures. In this case, since it's 1.17, we're just gonna round off. So our final answer is 1.2 times 10 to the power of negative 7 gram per cubic meter. This is it. We're done with the first question. Okay guys, so for the last question, before I proceed to I'll just make another video about second order reaction so that it'll split into 2. So the second question is, how long will it take for the concentration to decrease to 3.0 times 10 to the power of negative 7 gram per cubic meter? So guys, you need to take note of the following. So the initial concentration is much more greater than the final concentration, meaning that our final concentration, if you're asked to solve for the final concentration or AT, it's always less than the initial concentration. So the initial concentration is much more greater or much more bigger than the final concentration. So okay, again, we know using this given, we're asked to solve for time, and we can actually we can actually use this another equation, this one. Where was it? Yeah, this one. We can actually use this one or this one. For this case, let's try to use this one so guys you can familiar with different equations. So again, the second equation we're gonna use is ln of a sub t over a sub 0 is equal to negative kt. All you have to do is just divide negative k both sides, which is just ln of at over a sub 0 negative k. This is very simple, everyone. Okay, so using your calculator, guys. So again, using your calculator, press ln, then use the fraction bar, this one, and then of course 80 is at the top, so we're gonna use 3.0 times 10 to the power of negative 7, and our initial concentration is 5.0 times 10 to the power of negative 7. So guys, take note that we use you use this one from the given, and over negative 1.45, which gives us 0.35 here. This is it. So this is the end of the discussion for the first order reaction. I'll be continuing the second order reaction in the next video. Okay? So peace out, everyone. Bye.